Hello everyone. In this video, we are going to solve some gate problems. These are the problems from the network elements. So this is the first question from gate 2008. This is a 2-mark question. So the question is, assuming ideal elements in the circuit shown below, the voltage VAB will be dash. Okay, this is a circuit given. Here we have 1 ampere source, 5 volt source and a 2 ohms resistor. So now at this point, at this node, we have to find out the voltage. Okay. So we have to apply the KCL equation here. So if you see here, this is a voltage source in series with a resistor. So this voltage source in series with a resistor can be converted into a current source in parallel with the same resistor. While writing KCL, it is always advisable to convert a voltage source in series with a resistor into a current source in parallel with the same value of the resistor. Okay. So first we will convert this voltage source into a current source. So the current source value is given by Ohm's law. I is equal to V by R. So the rest of the elements will remain as such. That is, the 1 ampere source will remain as such. Okay. So now this point is A. Now this 2 ohms resistor which was in series will become in parallel with the current source. Now we have to mark the current source direction in the downward direction. Why? Because here this is positive terminal and above it is negative terminal. So it is always advisable to mark the current direction flowing from the positive terminal. Okay, so the current will be flowing in the downward direction. So the current value I is given by V by R. So here V value is 5 and R value is 2. So this will be equal to 2.5 ampere. So this is the current value. Here we have the node B. Okay. So this is a common node. So here we have to write a node equation. Okay. Here this is node VAB. So we have to find out the VAB voltage by using KCL equation. So Kirchhoff's current law. So Kirchhoff's current law states that at a particular node, sum of the incoming currents is equal to sum of the outgoing currents. Okay. So the current flowing through the resistors are assumed as outgoing currents. Always assume the currents flowing through the resistors as outgoing currents. Okay, then it will be easier for you to solve the problem. Now incoming current is given by the current direction only. The current direction is towards the node, flowing towards the node, then it is the incoming current. And if the current direction is flowing away, okay, if the direction is in the opposite direction, that is flowing away from the node, it is considered as outgoing current. So in this case, we have two current sources. One is flowing towards the node, another one is flowing away from the node. So we have incoming current as 1 ampere because it is flowing towards the node. And here we have outgoing currents. So 2.5 is the outgoing current, and then the current flowing through the resistor is assumed as outgoing. So again the current is given by Ohm's law, voltage divided by the resistance value. Okay. So 2.5 plus VAB by 2 is the outgoing current. Okay, sum of the outgoing currents. So by KCL, we can equate these two. That is 2.5 plus VAB by 2 equal to 1. Or we can write it as VAB by 2 is equal to 1 minus 2.5, which is equal to minus 1.5. Okay. On the left hand side, we have VAB by 2. So this can be written as VAB is equal to minus 1.5 into 2, which is nothing but minus 3 volts. So this is the answer. Okay, this is a simple straightforward question. So now we'll solve the second one. The second one is a similar problem only. The question is, in the circuit shown below, the voltage and current sources are ideal. The voltage V out across the current source in volts is dash. So this is again from gate 2016 and it is a 1-mark question. Okay. So here again we are going to use the Kirchhoff's current law only. So here we have one voltage source in series with the resistor. So we can convert this voltage source in series with the resistor into a current source in parallel with the same resistor. Okay. So now this 10 volt source is converted into a current source. So the direction, how we have to mark the direction, already we have discussed it. Okay. Always assume the direction of current flowing from the positive terminal. Okay. So if the positive terminal is below, then we have to mark it in the downward direction. Okay. Since it is in the upper leg, we have to mark it in this direction. Okay. So 10 volts divided by 2 ohms will give you current. So 5 ampere. So this 5 ampere current is in parallel with the same value of resistor 2 ohm. And then we have one more 5 ampere source. Okay. So now we have to find out the voltage V out. Okay. So this is 5 ampere again. So now this is a common node and this is one node here. So this is nothing but the nodal voltage P out. Okay. Now we have two current sources. So both the current sources are flowing towards the node. Okay. So both are incoming currents. And the outgoing current is nothing but the current flowing through this 2 ohms resistor. Always assume the current flowing through the resistors as outgoing, so that it will not, you will not get confused with that. So while writing KCL equation, we have to write down the sum of incoming currents and sum of outgoing currents at a particular node. Okay. So here we have two incoming currents, 5 amperes. So 5 plus 5 will get 10. So next outgoing current is nothing but the current flowing through the resistor. So it is given by Ohm's law, V by R. Okay, this is equation number 1 and this is equation number 2. So now we have to write the KCL equation. So we have to equate these two. So V out by 2 is equal to 10. Or V out is equal to 10 into 2, which is nothing but 20 ways. Now we'll solve the third one. So the question is, the power supplied by 25 volts source in the figure shown below is dash. So we have to find out the power in watts. This is again one more question. Okay. So here we have two sources, one voltage source, another one is the current source. So this current source is nothing but the current dependent current source. So this value depends on the current flowing through this particular branch, that is through R1. Okay. Here R1 and R2 values are unknown values, and voltage drop across this R1 is given and current flowing through this R2 is given. Okay. So we can either apply KVL or KCL for solving this problem. So now I'll apply KVL, which is easier to apply. So I'm redrawing the circuit here. So now here we are going to assume two currents. Since we have two meshes, we have to assume two currents, I1 and I2. So rest of the things are same. Here I is given as the current flowing through this R1. So since we have assumed I1 as the current flowing through this loop, here I is nothing but I1 in this case. Okay. And here it is 17 volts. And here current is 14 ampere flowing through R2, which is given the downward direction. Okay. There is no need for writing the mesh 1 equation. So we'll directly write mesh 2. If you see here in mesh 2, we have a current source on the outer periphery. So if a current source is present on the outer periphery, then it is defined as a super mesh. Okay. So we should not write the equation for this one. Instead, we have to equate this loop current to this current source value. Okay. So the direction, if you see the direction, this I2 is in the clockwise and it is flowing in the downward direction. And this current source is in the upward direction. Both are in the opposite directions. So I2 can be written as minus of 0.4 into I. Okay. So already we know that I is nothing but I1. So this can be written as minus 0.4 into I1. Okay. On rearranging this, we can write it as minus 0.4 I1 minus I2 equal to 0. Let this be equation 2. So now this branch current is given. Okay, 14 amperes and it is flowing in the downward direction. So this branch is lying in between mesh 1 and mesh 2, right? So this current 14 ampere can be either I1 minus I2 or I2 minus I1. Okay. So how will you decide I1 minus I2 or I2 minus I1? This mainly depends on the current direction only. So if you see here, I2 is flowing in the downward direction, which is same as that of 14 ampere source. Okay. So in that case, what we have to do is I1, we have to take I1 first And then we have to subtract I2 from I1. Okay, which is nothing but 14. So this is equation number 3. Okay. So now we can subtract these two equations so that I2 will get cancelled and we'll get I1 value directly. So why we are finding out I1? Because I1 is the current flowing through this 25 volt source. So we have to find out the power. Okay. So the power is nothing but V into I. So V value is 25 and so we have to find out this I1 value. Okay. So we'll write the second equation. We'll subtract these two equations. Okay. 2 minus 3. 2 minus 3. So we have to change the sign. So here minus. So this is minus. And this is plus. And this is minus. So I2 will get cancelled. This is minus 0.4 I1. This is minus I1. So minus I1 is something but minus 1, right? So we have to add these two. Minus 1.4 I1 equal to minus 14. So minus will get cancelled. So I1 is equal to 14 divided by 1.4, which is something but 10 ampere. Okay. So now we have found out the current flowing through this voltage source, and the voltage value is 20 times. So the power flowing through this 25 volt source is nothing but V into I, 25 into 10, which is equal to 250 watts. So this is the answer. So next we will solve the fourth one. In the given circuit, for the voltage Vy to be 0, the value of beta should be dash. Okay. Here we have 6 volt source and 1 ohm, 2 ohms, 3 ohms and 4 ohms resistors and one current source, and this is again voltage dependent voltage source. Okay. So now we have to solve this problem and find out the value of beta. Okay. We have given two node voltages Vx and Vy. So we'll apply node analysis over here. Okay. So let us assume this is as node 1 and this as node 2. Node 1 voltage is Vx and node 2 voltage is Vy. Okay. So we'll write two node equations and solve them to find the value of beta. Okay. So if you see here, this is a voltage source in series with the resistor. So we can convert this voltage source into current source. Okay. So the direction of the current source should be marked always from the positive terminal. Okay. So it should be marked in this direction. So this 6 divided by 1 will be 6 only. So 6 ampere. And this 1 ohm source will come in parallel with the current source. And this Vx will remain the same. And here we have 2 ohms. Here we have 4 ohms. And here again, one current source, 2 ampere. And this dependent voltage source cannot be converted into current source. So we will keep it as such and write the equation. Okay, beta value is unknown also. Okay. So I have redrawn the circuit by converting the 6 volt source into a current source. So remaining things are same. So now we'll write the equation for node 1. So in node 1, we have to write both the incoming currents as well as the outgoing currents. So always assume the currents flowing through the resistors as outgoing currents. Okay. So incoming current should be written with respect to the current source only if the current source is flowing towards the node. So if you see here in node 1, we have 1 ohms, 4 ohms and 2 ohms resistors, and we have one current source. So this current source direction is flowing towards node 1. So it is the incoming current. Okay, the direction is towards the node means incoming. So next we have to write all the outgoing currents and add them. So sum of the outgoing currents. Now the current flowing through this 1 ohm resistor. Okay. So this is voltage. So this is a common node they have given. So this is 0 volts. So the voltage across this particular resistor will be Vx minus 0 or simply Vx. Current I by Ohm's law is V by R. Okay, so Vx divided by 1 will be the current flowing through this particular 1 ohm resistor. So Vx by 1 plus current flowing through this 4 ohm resistor is again Vx divided by 4. So next this 2 ohms resistor is lying in between node 1 and node 2. So the voltage is Vx minus V by R, Vy minus Vx. So in this case, we are writing for node 1. So we have to consider this as Vx minus Vy divided by 2. Okay. So on simplification, we will write it as Vx by 1 is nothing but Vx. Vx by 4 is 0.25 Vx. And again, this can be written as Vx by 2 minus Vy by 2. So Vx by 2 is nothing but 0.5 Vx minus 0.5 Vy. Okay. So on simplification, we will get the output or outgoing current as 1.75 Vx minus 0.5 Vy. So now we have to write the KCL equation. The KCL equation means in a particular node, sum of the outgoing current is equal to sum of the incoming current. So KCL equation for this case is 1.75 Vx minus 0.5 Vy equal to 6. So this is equation number 1. Okay. So next we'll write the equation for node 2. So again for node 2 we have to write the incoming current as well as the outgoing current. If you see node 2, the elements connected are 2 ohms resistor, 3 ohms resistor. Here this is a 2 ampere source flowing towards the node and this is the voltage source. Okay, this is voltage dependent voltage source. So now the incoming current is written with respect to current source only. So this is 2 ampere here. So next we have to write down all the outgoing currents. So currents flowing through the resistors are assumed as outgoing currents as we have discussed already. So first we'll write the current flowing through this 2 ohms resistor. So this voltage across this 2 ohms resistor is Vy minus Vx. So while writing for node 1 we have written it as Vx minus Vy. Now we have to write it as Vy minus Vx divided by 2. So next and this 3 ohms resistor is connected in between Vy as well as this voltage source is connected at one end. One end we have this voltage source and on the other end we have this Vy. So the total voltage should be written as Vy minus beta into Vx divided by 3. Okay. So on simplification, Vy by 2 will be 0.5 Vy. Again minus Vx by 2 will be minus 0.5 Vx. Plus here Vy by 3. Vy by 3 is nothing but 0.33 Vy minus this is beta by 3 into Vx. So 1 by 3 is again 0.33 beta into Vx. Okay. So now we'll segregate the coefficients of Vx and Vy and write it separately. So for Vx we have the coefficients minus 0.5 and minus 0.33 beta. So I'm taking minus outside. So the remaining terms are 0.5 plus 0.33 beta Vx and then Vy coefficients. Vy coefficients we have 0.5 and 0.33. So we have to add these two. So this will come to be 0.83 Vy. So now the KCL equation for node 2 will be minus of 0.5 plus 0.33 beta into Vx plus 0.833 Vy. Vy will be equal to 2. So this is equation number 2. Okay. So now in the problem it is given as Vy is 0. Okay. So we are going to substitute Vy is equal to 0 in both equations 1 and 2. Now we will substitute Vy equal to 0 in both equations 1 and 2. Okay, first we will substitute in 1. So if we substitute in first equation, we get 1.75 Vx minus 0.5 into 0 equal to 6 or 1.75 Vx is equal to 6 and Vx is equal to 6 divided by 1.75 which is equal to 3.4285 volts. Okay, so this is Vx value. So now we will substitute Vx is equal to 3.4285 volts and Vy is equal to 0 in equation number 2 to find out the value of beta. Okay. So now we'll substitute both the values minus of 0.5 plus 0.33 beta multiplied by Vx. Vx is nothing but 3.4285 4.85 plus 0.83 into 0 equal to 2. So this term will become 0. So the remaining terms are minus of 0.5 plus 0.33 beta into 3.4285 equal to 2. So we can take this term towards the right hand side and we simplify this. Multiply this minus inside. So minus 0.5 minus 0.33 beta equal to 2 divided by 3.4285. Okay. So this will become minus 0.5 minus 0.33 beta equal to 0.583345. So this can be again written as 0.33 beta is equal to 0.583345 plus 0.5. Okay, bringing this term towards the right side. So this will become 1.08334. So this side we have 0.33 beta. So now beta is equal to 1.08334 divided by minus 0.33, which is something but minus of 3.2828. Okay, this is the answer. Now the next question is, in the figure shown below, the value of R in ohms is dash. Okay. So here this is a circuit. Here we have 3 resistors, 2 10 ohms and 1 unknown value. So this R value we have to find out, and this is 100 volts also. So now I will redraw the circuit here. We can either apply Kirchhoff's voltage law or Kirchhoff's current law to find out the value of R. So here for simplicity I will apply Kirchhoff's voltage law only. Okay, Kirchhoff's voltage law or mesh analysis. So here we have 2 meshes. So we can assume 2 mesh currents I1 and I2. So always assume the currents in clockwise directions. Okay, because it will minimize certain errors. So irrespective of the directions given, you always assume the unknown values or the loop currents as flowing in the clockwise directions only. So first we'll write the equation for mesh 1. For mesh 1, we have to write both the voltage rise as well as the voltage drop. So the voltage rise is always written with respect to this voltage source. So if the assumed current direction is from negative to positive, then this is voltage rise. So in this case, the current I1 is flowing from negative to positive with respect to this 100 volt source. So this 100 volt source is considered as voltage rise, and the voltages across the resistors are considered as voltage drop only. Okay. So now we have 2 resistors up. Okay, 2 10 ohms resistors. So we'll write down the sum of voltage drops. So current flowing through this 10 ohms resistor is nothing but 10 in I1. So the voltage drop is 10 into I1. Similarly, the other 10 ohms resistor is lying in between mesh 1 and mesh 2. Okay. So in mesh 1, the current I1 is flowing in the downward direction. In mesh 2, current I2 is flowing in the upward direction. That is, both are in the opposite directions. So the net current can be I1 minus I2 or I2 minus I1. While writing for mesh 1, we have to consider this as I1 minus I2. Okay, if we are writing for mesh 2, then we have to write it as I2 minus I1. So now on simplification, we will get 20 I1 minus 10 I2. Okay, this is sum of the voltage drop. Now if we write the KVL equation, sum of the voltage rise is equal to sum of the voltage drop. Okay. So 20 I1 minus 10 I2 equal to 100. So this is equation number 1. So now we'll write the equation for mesh 2. In mesh 2, we do not have any voltage source. So we can directly write the voltage rise as 0. And then we have to write down the voltage drops. We have 2 resistors. So we'll write the voltage drop across these 2 resistors and we'll add that. Okay, so sum of the voltage drop is equal to voltage drop across 10 ohms resistor is nothing but 10 into I2 minus I1. Okay, while writing for equation 1, we have written it as I1 minus I2. So now for mesh 2, we have to write it as I2 minus I1. Again, current flowing through this R is I2. So I2 into R. Okay. So on simplification, we get minus 10 I1 plus 10 plus R into I2. So this is sum of the voltage drop. So now the KVL equation for mesh 2 is minus 10 I1 plus 10 plus R into I2 equal to 0. So this is the second equation. So in the circuit itself, it is given that the current flowing through this particular branch is 2 ampere. So we have assumed I2 as the current flowing through this branch, and both this I2 and 2 ampere source are in the same direction, sir. So we can write it as I2 is equal to 2 ampere. Okay, this is the given value given. Now we'll substitute I2 in equation number 2 so that we'll get the value of I1 parity. Okay, so substituting equation number 3 in equation number 2. So now equation 2 becomes minus 10 I1 plus 10 plus R into 2 equal to 0. Okay, so this is equal to minus 10 I1 plus 20 plus 2R equal to 0. So minus 10 I1 is equal to, so taking these two terms towards the right hand side, we can write it as minus 20 minus 2R. So taking minus outside again, this can be written as 20 plus 2R. Minus of 20 plus 2R, minus will get cancelled. So I1 is equal to 20 plus 2R divided by 10, which is nothing but 2 plus 0.2R. So this is I1 value in terms of R. Okay. So let this be equation number 4. Okay. So now we'll substitute this equation 4 in equation 1. Okay. Substituting both I1 value as well as I2 value. Okay. From equation number 3, we have I2 is equal to 2, and from equation we have I1 is equal to 2 plus 0.2 into R. So now we are going to substitute both the equation number 3 and 4 in equation number 1. Okay. So 20 I1 minus 10 I2 equal to 100. So this is equation number 1. Already we have derived this. So now we are substituting I1 value. So I1, which is nothing but 2 plus 0.2 R, and I2 value, which is nothing but 2 in equation number 1. Okay. So now the equation will become 20 into 2 plus 0.2 R minus 10 into 2 equal to 100. So again we'll multiply this one. So 20 into 2, 40 plus 20 into 0.2 4 R minus 20 equal to 100. So 40 plus 4R equal to, taking this 20 this side, so this will be 120. So now 4R is equal to 120 minus 40, which is nothing but 80. So R is equal to 80 divided by 4, which is nothing but 20 ohms. So the R value is 20.